Okay, we're back, and let's do an example here. And this example is to point out something that might seem kind of obvious, but I think it's still worth doing a quick little example. And that is our definition here says a vector subspace is a subset that's itself a vector space. Well, of course, this suggests that there are subsets of a vector space that aren't themselves vector spaces, which of course is true, but let's just do an example to see a particular case like that, because this is actually going to be a little bit instructive. So let's take as our example, let's take a situation where n is 2 and m is just 1, and so we're back in R2 with a homogeneous linear equation system, but it's only one equation because m is 1. And so let's make our example look like this. Here's x1, here's x2, and I want the example to be one where we have S is the set of all vectors in Rn such that, and now I'm going to do this in general, but of course I'm going to write the example in R2, where Ax equals B, where B is not the 0 vector. So in this n equals 2, m equals 1 case, that says A1x1 plus A2x2 equals B, which is not 0. And so the set of solutions is again going to be a line, but it's not going to be a line through the origin. It's going to be a line that maybe looks something like this. And so this would be the set S in this case. And just note that that the origin, the 0 vector, is not in the set of solutions. That is, if I put x1 and x2 in here, the equation comes up 0, which is not B, because B is itself not 0. So here we have a subset. So let's write that in here. We have S is a subset of the vector space R2, of course. Doesn't contain the origin, and that's enough, it turns out, to tell me that this is not actually a subspace. It's a subset, but it's not a subspace. Now, that's because I know that subspaces have to contain the 0 vector. So I could prove that in this case, but what I'm going to do is use this as motivation for a more general remark that says any subset that's actually a subspace has to contain the 0 vector. So we'll say if S is a subspace of a vector space V, then S has to include the 0 vector, and that's the 0 vector of V. Easy to prove. Let's start by saying that if S is a subspace, therefore it's a vector space itself. Therefore, in our definition of a vector space, S can play the role of V throughout. Now, granted, there's a V here that's the parent vector space, but we're looking at the subset S and saying it's a vector space itself, so S plays the role of V in this definition over here, and in particular, look at V7. V7 says there exists a vector x hat in V, meaning there exists a vector x hat in S because S is playing the role of V. That means that x hat is in S, where x hat is the element that's in V. In particular, that means that the element of V, that's the additive identity, has to be in S. And so actually that by itself tells me that the 0 vector is going to have to be in S because x hat is a 0 vector. Another way I can see that is to say this tells me that S is non-empty, and so from that I have that lambda x hat has to be the 0 vector for lambda equals 0. So again, therefore, V2 tells me that this 0 vector is in S because V2 tells me that lambda times x hat is in S. So that yields also that the 0 vector is in S. So either way I do this, I can establish immediately that if I have a subspace of a vector space, that subspace has to contain the 0 vector, the origin of the parent vector space. And now I said that what we want to do here is we want to come up with some easier conditions that will make it easier to check whether a set is a subspace, whether a subset of a vector space is a subspace, than having to check all 8 of the properties here. This gives me one sort of a check in that if I can see that the 0 vector is not in my subset, I immediately know it's not a subspace. But it doesn't really go the other way. Knowing that the 0 vector is in the subset is by no means enough to tell me that subset's a vector space or a subspace of the parent vector space. But it does turn out that as long as we know that our subset S, and so that's what we're doing here, is we're saying that what I want to do is I have now some subset of a vector space. The V I know is a vector space. And so I'm questioning whether this subset is a vector space. So I'm questioning whether that set S can play the role of V and all 8 conditions are satisfied. As it turns out that we can easily prove a theorem that gives us these easier conditions. And we have that theorem here. It tells us that a subset of a vector space, call it S, with the V operations, the operations it inherits from the parent vector space, that is a subspace, a vector space in its own right, if and only if it's non-empty, satisfies V1, satisfies V2. Now let's look at this in a little more detail. It says if and only if. So in particular, it's saying that if I have a subspace, it has to be non-empty and it has to satisfy V1 and V2, but we already know that. If I have a subspace, then by definition, it's a vector space in its own right, and therefore it satisfies V7, so it's non-empty, as we found here, and of course it satisfies V1 and V2, because if it's a vector space in its own right, it satisfies V1 through V8. So if we have a subset that is a subspace, of course, it's non-empty and satisfies V1 and V2. We need to go the other way. So we need to prove that if we have a subset that just satisfies V1 and V2 and is non-empty, forget about V3 through V8. If it just does those things, it is a vector space in its own right, therefore a subspace, therefore it does satisfy V through V8, V3 through V8, but we don't have to prove it if we have this theorem. Okay, now let's just notice one more thing about this theorem. The theorem says that our subset of a vector space will be a vector space in its own right if it simply satisfies just V1 and V2 and is non-empty. So what about that non-empty part in there? So do we really need that? It seems as if it satisfies V1 and V2, it couldn't be empty. So the empty set's already ruled out. That's actually not the case, as we'll just see here. And it will take us a moment or two to say, well, could the empty set satisfy both V1 and V2? If it could, then this theorem, without the non-empty part, would say the empty set is a vector space in its own right. But we already know that the empty set couldn't be a vector space because to be a vector space, it has to be non-empty. So the question here is, could the empty set satisfy V1 and V2 and therefore be a vector space if we left out the non-empty part, which would be wrong. So let's just look at V1 here and let's just ask, is it the case that if we have x and y in the empty set, that implies x plus y is in the empty set? Because if that can't be, and if the same thing if V2 can't be, then we don't need that non-empty part in there. Let's just check this. Certainly, the consequent of this implication is always false because no vector is in, whoops, that's supposed to be the empty set. Let's take that off and make that the empty set there, okay. Certainly, no vector is an element of the empty set, so the consequence is always false for any vectors, x and y. So this looks a little daunting for V1 to be true, but of course, the antecedent is always false as well. We could never, for any x and y, they're not going to be in the empty set because the empty set doesn't have any vectors in it, doesn't have anything in it. So that means that the empty set satisfies V1, and the empty set, of course, satisfies V2 as well. I won't write all that out, but the empty set satisfies V2 as well. So that would mean if we drop the non-empty qualification here, this theorem would say that the empty set's a vector space, in its own right, a subspace of V. And we know that is not the case from our definition of a vector space, because the definition of a vector space says in V7, for example, that there exists an x hat in the vector space. The vector space can't be empty. The empty set is not a vector space, period. So you're going to provide a proof of this theorem yourself as an exercise. And now let's take this off and let's do a couple of more examples. Okay, so now we're going to conclude by doing a couple of examples, and actually the two examples will turn into three examples of subspaces. And so let's do a first example. And this example is going to be something called C of R. And that is the set of all continuous functions from R to R. So you'll remember that we have used, in fact, I guess as recently as the previous lecture, we used the set script f of any domain was the set of all functions on that domain into R, all real valued functions. So here, the set script f of R is the set of all functions from R to R, the set of all real functions or real valued functions on R. And so the set of continuous real functions on R, or real functions, is clearly a subset of f of R. So here we have a situation like what we saw earlier in the lecture, where we now have a vector space. We know this is a vector space, and we have a subset of the vector space, and we want to determine whether that subset is a vector space in its own right, and therefore a subspace, a vector subspace here. How would we go about proving that? Again, let me suggest that you pause the video here for a few moments and you think about how would you go about verifying that this set of continuous functions is a vector subspace of f of r. That is, that it's a vector space in its own right. So you might pause this for just a moment here and think about that. So now I'm going to assume that you've returned from pausing the video and maybe going to the refrigerator and getting a soft drink or a beer, and you've thought about this a little bit. And so now let's see, how would we go about doing this? Well, what do we have to do? We have to establish it's a subspace. We have to establish that it's non-empty, that it satisfies V1 and V2. Maybe I should say V1 and V2 and non-empty. Okay? Well, certainly this set's non-empty because the function that's 0 everywhere in R, that assigns every real number 0, that's a continuous function. And so it's in here. So it's clearly non-empty. No problem there. Lots of continuous functions. What about establishing V1 and V2? What do we have to do? What we have to do is say, we have to say for any pair of functions in C of R, we have to establish that if these two functions are in here, then f plus g is in C of R. That is, we have to establish that the sum of these two real valued functions is itself a continuous function. To put it another way, we would want to establish that the sum of any two continuous real functions is itself a continuous real function. That's something that you probably encountered maybe even in your first calculus course, perhaps, that a theorem or a result that said the sum of any two continuous functions is itself a continuous function. That's what we have to prove here. And so if we've already proved it somewhere, we've got that. Same thing for for scalar multiplication. We have to establish that if lambda is in R, well, we already know that if lambda is in R, and if f is in C of R, we have to verify that then lambda f is in C of R. That is, we have to prove that a scalar multiple of any continuous function is itself a continuous function. Again, something you might well have done in your undergraduate mathematics, perhaps even in the first calculus course, that any multiple of a continuous function is itself a continuous function. So if we establish those two facts, that you add continuous functions, you get a continuous function, take a multiple of a continuous function, it's a continuous function, we've established then V1 and V2, and we know this is a non-empty set, so it's clear that then our theorem that said all we have to do is verify V1, V2, and non-emptiness, that holds here. And so C of R is a vector subspace of f of R. Second example. Let's let B of R be the set of all bounded functions, real functions. So f from R to R. Now, we haven't actually defined bounded functions. I don't know if we'll actually do that in this course. You'll probably do that in the next course you do on mathematics. Straightforward. In fact, I can say what the definition is here. A function's bounded. A function from R to R is bounded if, in fact, the range of the function is a bounded interval. Let's say an interval from A to B, a subset of R. So if the range of the function is a bounded subset of R, it doesn't go off to infinity or minus infinity, then it's a bounded function. So the set of all bounded functions they're all functions from R to R. So clearly, the set of all bounded functions from R to R is a subset of f of R as well, because they're all functions from R to R. So here again, we have a subset of a vector space. It's non-empty because, again, the function that assigns to every real number 0, the constant function 0 everywhere, that's bounded, of course. And so this is a non-empty set, contains that function. And again, all we have to do to verify that this is a subspace, a vector space in its own right, is to establish V1 and V2. And for that, we have to establish, and I'm not going to write this all down now, we have to establish that for any two functions in B of R, any two bounded functions, the sum function is a bounded function. I'll write it down. It'll just take a second here. F and G in B of R implies F plus G in B of R. That would be V1, and V2 would be lambda in R, and F in B of R implies lambda F in B of R. Again, both of these, once we have our definition of a bounded function, as I described, really easy, simple to prove both V1 and V2, to verify both V1 and V2 for the set B of R, and it's non-empty. So that is also a vector subspace of the same vector space here, the set of all functions from R to R. Now, they're both of these sets are subspaces, vector subspaces. Notice that neither one's a subset of the other. That is, there are plenty of continuous functions that are not bounded. Just take the function f of x equals x. That's not bounded because x gets arbitrarily large, both positive and negative. So there are plenty of continuous functions that aren't bounded, so this is not a subset of B of R. There are plenty of bounded functions that are not continuous. You can make up simple functions that are bounded and not continuous. Just take a function that's 0 on all the negative real numbers and 1 on all the positive real numbers, and it can be anything at 0. It'll be not continuous. It'll certainly be bounded. Well, yeah, it can be anything here. It'll still be bounded. So there are plenty of bounded functions that aren't continuous. So there are functions in B of R that aren't in here. There are functions in C of R that aren't in here. All those functions are in F of R. And so let's now look at a third example, which I'm going to call C sub B of R, which is the intersection of C of R and B of R, the set of all bounded continuous functions f from R to R. I maintain that that is a vector space in its own right as a subset of this, clearly CB of R is a subset of F of R, which you can of course see directly because it consists only of functions from R to R, or you can see it indirectly because each of these is a subset of F of R, and so the intersection of the two would have to be a subset of F of R. And so I maintain that this subset of F of R is a vector space in its own right, that is, a vector subspace. Now, I could prove this by verifying V1 to V8. We already know that instead I could prove it a little more simply by just verifying that this set is non-empty and satisfies V1 and V2. And of course, the fact it's non-empty is clear enough because it's the intersection of these two sets. Well, that wouldn't by itself say that it's non-empty, but as I already indicated, that the zero function is in both. It's bounded, it's continuous, so it would be. So it's non-empty, that's easy enough. So I could verify V1 and V2, but what I'm going to do is take a different approach. I'm going to say I have a set that is the intersection of two vector subspaces of the same vector space, and I'm going to suggest that that in itself, independent of the fact that these happen to be these particular subspaces, that enough will tell me that this is a vector subspace. So that is a theorem, and it's a theorem about vector spaces and subspaces in general. So the theorem is going to be if S1 and S2 are both subspaces of a vector space V, of course the same vector space, both subspaces of the same vector space, then S1 intersect S2 is also a subspace of V, and I guess I should add with the V operations, of course, with the operations that S1 and S2 inherit from the parent vector space V. So let's see if we can prove this. But again, before proving it, let me emphasize, here I've got a pair of vector subspaces of F of R, and I'm suggesting that I could prove that this intersection is itself a subspace, a vector space in its own right. But instead of proving that for this specific case, and then having to do it again the next time I see the intersection of two subspaces, I'm just going to say, let's just go straight to the heart of things and prove a theorem about vector spaces and their subspaces that will be a theorem that will be in our catalog of theorems about vector spaces that then we can pull out and use whenever we encounter a vector space and some subspaces. So the proof here, let's say we're going to assume that S1 and S2 are both subspaces. And so I need to verify that this is a subspace. I'll leave aside for the moment the question whether it's non-empty. And let's look at V1. We have to verify V1. Okay, so we need to assume that we have assume that we have an X and a Y. Let me actually say this a little bit differently. No, that's good. If we have an X and a Y in S1 intersect S2, that implies then we have X in S1 intersect S2. In fact, let's say it a different way here. That means that we have X and Y in S1. Therefore, X plus Y is in S1. Similarly, we have X and Y in S2. Therefore, X plus Y is in S2. And both of these come from the fact that S1 is a vector space in its own right, a subspace. S2 is a vector space in its own right, a subspace. And these two together tell me that X plus Y is in S1 intersect S2. And that establishes V1. If I've got vectors in S1 intersect S2, then X plus Y is in S1 plus S2. And of course, V2 is equally easy. We'll say, assume lambda is in R and X is in S1 intersect S2. This appears to be perhaps running out. So let's go to a a different marker here. Then we have, if lambda is in R and x is in S1 intersect S2, then lambda x1 is in S1 because x is in S1 intersect S2, so x is in S1. And therefore, since S1 is a subspace, lambda x1 is in S1. And lambda x2 is in S2. Whoa! There is no x1 and x2 here, so let's get that 1 out of there. And let's get this 2 out of here. Okay, we've got x in S1, which is itself a subspace, so lambda x is in S1. X is in S2, this is the intersection, so lambda x is in S2, and of course, therefore, it follows that lambda x is in S1 intersect S2 because it's in both S1 and S2, and that, well, that completes the proof, except we haven't shown that the that S1 intersect S2 is non-empty. So how would we show that it's non-empty? What would be a simple way to show it's non-empty? Think about that for a second. Well, we've already shown in a remark that if we have a subspace, then the 0 vector from the parent vector space has to be in there. So that means the 0 vector's in here, and the 0 vector's in here. So that means the 0 vector is in the intersection, so it's non-empty. So we have it non-empty as well. In fact, not just non-empty, the 0 vector is in there. So that establishes then that indeed the intersection of any two subspaces of a vector space is itself a vector space. So a useful theorem, a theorem that we can put into our little catalog of theorems about vector spaces and subspaces that we can now pull out and use whenever we encounter subspaces of vector spaces. So actually very useful. We'll see this multiple times again. So that's it for vector spaces and subspaces. Next time we will do a little bit more with vector spaces. We'll go on, I think, and talk about linear combinations, linear functions in vector spaces. So that's where we'll go next time, and we'll see you next time.